So for pedicle transformer, you can see that here we do have the lead gauge flux circulating in around the winding. So in theory, all the magnetic flux will go through the main core, like in this path. But however, because this magnetic core is not infinity permeability, it may not able to contain all the magnetic flux inside the core. And also there will be the winding is not perfectly wired across the whole magnetic core. So that means there will be some fringe field. Fringe field around in here, as you can see in here. So this kind of magnetic flux, if it is not linking the main core, we call it the lead gauge flux. So this lead gauge flux will therefore contribute as the lead gauge inductance, which usually connected in series with the transformer. So that's a really common phenomenon for all the transformer or magnetic systems. So that's why you can see that in here. The flux linkage, that means the lead gauge flux here, connected with how many number of turns in the primary per unit of the current will give us about the lead gauge. So that's the basic definition for inductor. So that means in primary side, we have the lead gauge for the primary side, and the secondary side, we also have similar lead gauge. And then if you look into the equivalent circuitry, you can find that the winding resistance, which is copper resistance, which basically mainly comes from the copper resistance, will be called R1 from the primary side, and secondary side is R2, and it also have its own lead gauge component. So it looks like these two are connected in series. And also in the secondary side as well. Between them, we can just using an ideal transformer to represent the whole model. This is a really common model we can see every day from all the literature or all the internet material. And then another component we can see that will be so-called the magnetizing. Later on, we'll discuss more detail about it. So for magnetizing, because we do have the copper winding wire on the main core, and then the magnetic material inside the core will expose to the eddy current and also hysteresis losses. So this losses component will therefore represent by the RC1, which is the resistive core loss, the real component, so then mainly about the core loss. Another one is XM1, which is the magnetizing inductance of the transformer. So these two are mainly contributed by the winding, which is the more look like the inductance of the transformer. And then this one more look like all the losses component for the inductor. So these two are applied in a form of parallel to the transformer core. So these are also really famous so-called the T model of the transformer. So now then you can see this model. We got the series component due to the lead gauge and also the copper losses. Secondary side, we also have the copper losses and also lead gauge component. In parallel with the connection, we can see the core loss component plus the magnetizing component. Of course, this is in the winding in the secondary side. We usually have a transformer, ideal transformer, to represent the connection. So that's how we usually see that. And then the relationship between them all are related by the turns ratio. In most of the calculation or modeling, we tend to refer all the parameters in the secondary side to the primary side, which you can see in this model. That's a very common model. Probably you all know that. I may not spend too much time on here. Then you can see that the voltage, when we refer the secondary side to the primary side, we call it E2 dash. So this voltage must be equal to E1 because this is a transformer. Although between them, you got the N ratio relationship. And so that's how we see the voltage relationship with the N, which is the turn ratio. And the current ratio will be also related to n, but now be an inverse proportion to n. And we can also find that the impedance, when we refer to the primary side, anything referred to the primary side, we got a dash here. And then the parameter is n squared, proportion n squared. So how that n squared come from? Mainly will come relate to the component voltage and current. Both of them has carry the n, so add together become n squared. So that's a really common phenomenon for all the textbooks. I don't derive them here, but you can really easily get this information from all the material everywhere. I just need you to recall your memory. Yeah. So now then, the model will look like this one. So that's the most common T model we can use for transformer. So then magnetizing, leakage component. So this is too simple, so that's why I don't go through it in too much detail. So the test usually including the low test and also the so-called short circuit test. So these two tests are commonly being used for obtaining the transformer parameter. Then you have low test, that means the secondary side will not connect to anything. If you don't connect to anything, then you can see that there will be really few current pass through this component, the leakage component, because presumably if open circuitry, no current pass through the secondary side. So that means if no current pass through the secondary side, this current must be really small. And then in this case, most of current pass through here will be more flow through the magnetizing component. We usually also assume the primary side, the leakage and resistance, because it got very few current pass through, the work drop on this component will be negligible. And so in this case, most of applied voltage, we tend to apply that on the magnetic core. So you see in this case, the open circuit test just look like a transformer without any connection in the secondary side. So that means most of the applied voltage more look like applied directly to the magnetic core winding, magnetizing winding. So that's why we assume this will be negligible, these losses on the primary side, and secondary side, of course, no connection. So that means we can use applied voltage and measure the current to get the parameter for R and X component. So that's commonly method being used. Of course, for the short circuit test, we tend to short the secondary side in here. Now in this T model, we make it simpler because when under the short circuit, there's a large current flowing through the series path. And the short circuit test, we usually tend to use a really low amount of current, small current to do that, because we don't want to damage the winding. Short circuit, only a few volts usually. So this tiny voltage will not cause any problem for the magnetizing. So I assume the current here will be really, really small. You can see that usually transformer 100 volt, 200 volt. Short circuit test, we only use just a few volts. So that means the current in here will be negligible. Most of current we can assume that pass through the leakage. So from here, we can therefore work out the measure the voltage, measure the current, and then we can get the R and X component just simply by Ohm's law, right? But one thing you can see that for short circuit test, we're not able to differentiate R and R2 dash. I think you all know that. So in this case, how are we going to measure or estimate individual component? R1 is the primary side, R2 dash is the secondary side. So we can only measure the total, right? Yes. So how do we know which one is which? Can we measure it? Can we estimate which one is which? I think you all work on transformer. That's a really basic question in the undergraduate, right?
What's the question?
We can only get, because when we measure the voltage current here, we can therefore calculate the impedance for sure. Just simple Ohm's law, right? And other than we only know this and that, but we don't know individual component or individual component for X, Y. How are we going to know which one is which? Can we get the primary resistance or secondary resistance? We only know the total. We don't know the individual, separate parameter. So how are we going to know that? Do you get my question?
No, no what?
Huh? Do you understand my question?
No, get what?
You don't
So I
get my question?
miss the question. Yeah.
Okay, yeah. I said under the short circuit test,
Yeah.
we apply certain voltage and measure the current. That's why we know the impedance. That impedance is this one.
Yeah.
Which means we can therefore know the R eq1 and X eq1 for sure, because we have voltage current, we can get that. But however, we don't know individual component. We can only know the total. We know the total here. But this one responsible for the primary side.
Yeah.
This one responsible for the secondary side. Can we any test or can we separate these two in the testing? That's my question. I think you have, everybody has done the short circuit test in the undergraduate, right? It's a really basic question. So what do you think? Can we do that? If we have the definition, if you got a primary side. Of course, we can service.
Yeah, so if you have the definition, we can differentiate those, right?
Can you?
R1 equals n squared R2, something like that. No. And the definition.
I think for reciprocal part may be quite possible. We can just tell me so and the copper size to do that. Because we can calculate this copper with this diameter, this copper diameter, this diameter. We can relatively calculate the relative portion between them. But the leakage component will be relatively difficult because leakage relates a lot of fringe field and how we do winding. We may not able to estimate properly, but we can only know the total. But however, in most of the scenario, because these two winding, we are trying to make them the Ni for the winding must be equal on either side. So that it will say when the R2 refer to the primary side, R1 should equal to R2 dash. Because the current ratio between them, we should use a proper copper size to do the same job. So in this case, we won't use, we're just using the sufficient current density. The current density between the primary winding and secondary winding should be the same. Because the basic how we wind a transformer. We won't use primary side, we use 3M, and secondary side, we don't use 30M. We use same current density. And then when the transformer transform the current, then when the current is larger, we're still using the same current density. So the resistance will therefore make the primary side and secondary side will be actually the same resistance. You can go back home to do some quick calculation. Then you know that under the proper design, if we use the same current density, R1 should equal to R2 dash. That's true for all the transformer. That's why, of course, many textbooks or internet material, they don't tell you why, but they only tell you, oh, we assume R1 equal to R2 dash. But the reason behind is mainly because we are using the same current density anyway. But if you're not using the same current density, then R1 will not equal to R2 dash. Then you have to use some kind of ratio to recalculate that. But XL1 and XL2 dash would be difficult to, although we use assume them to be equal anyway, but of course they cannot be exactly equal. But that's how so short circuit also has some limitation because we're not quite sure how to get a separate parameter exactly. In order to get the exact measurement, then you need to go to high level, high frequency magnetic. Then you come to me to do a PhD research. Then you know how to measure separate components, right? Much more for this kind of the master level, PhD level, you can't do that. Anyway, so here you just follow most of textbook. Internet material assume them to be equal. So that's how the other equation, we use it for well-designed transformer, we assume them equal because the same current density, the same kind of winding pattern.
So this is the condition. If we have same current density, then R1 should be equal to, can be equal to like R2.
If my question become more complicated, their current density not equal, then will be more complicated. They are not equal. Only when the current density equal. But usually for winding a transformer, the current density must be equal. We won't wasting our money to putting too much copper there. We're just using sufficient copper for that particular current. So that's how we come up with the
If less winding on one side, more winding on the other side, still you are saying current density we give
still same current density. But you see, the turn ratio will show you how many number of turns anyway. Yeah. So that means when you have step-up transformer, you got more winding and secondary side, but the current become less. Yeah.
overall
Yeah.
current would be.
Yeah, current become less. And then that's why, of course, the resistance will be higher, but when they refer to the primary side, you got n squared. So that's why they also make them become equal. So you can calculate more exactly. You can find that under this ideal design condition, R1 equal to R2 dash anyway. Because we take account with all the turns ratio, equal current density. Then happen to be everything equal. Yeah. That's how we call the well-designed transformer. Of course, for some random design, you don't care that you use the same copper, same diameter of copper, it won't be the case. But proper design, you can see that if step transformer, we use thicker copper on the primary side, and then we use a thinner copper on the secondary side. That's how we come up with this kind of the conclusion anyway. So that's why many textbooks, they just say, oh, I should R1, you are R2 dash. They didn't tell you exactly why is that? Because we're just using ideal transformer for the design. But when I have been doing magnetic for many, many years, so the lead gauge will be really complicated to assume them to be equal anyway. I don't think they're equal. But for simple analysis, I assume them equal will be fair enough because all the lead gauge from this T model, right? When the current pass through, it passes through the both component anyway. We don't really need to separate them. Yeah, because when we only need to know the total magnetizing inductance and total series component of inductance, that will be good enough for our calculation. So that means in a way, we don't need to separate them. But if you deliberately like to do that, then you need to have a more deep analysis. Anyway, so that finished about the short circuit test and also the open circuit test. These two are really major material for all the transformer analysis. But we have done that in the undergraduate, so we viewed it so that you understand some phenomenon. And in here, I just tell you they are not equal. But the textbook say they were equal, so at the moment we say they're equal. So final remark will be this chapter 2, provide you a basic concept and revision for your transformer. I think you all know that. So basically, we have transformer turn ratio, voltage ratio, relationship. We also introduce to you the magnetizing component, and that's mainly about the core loss, and also the cell inductance, which also more look like the magnetizing component. So the magnetizing inductance XM are more look like the cell inductance for a transformer. But the series component are actually is the resistive losses due to copper and also the lead gauge component. The lead gauge component appear to be in series with the winding. So we use the short circuit test, open circuit test, then estimate the component. So this is million of the material for short circuit test, open circuit test, and transformer. So you can go through them to understand more if you like to. I think you're all good at that. So don't need to use any textbook. All the textbooks are too simple, too expensive. Okay, that's it.